Hello and most welcome to a lecture about chaos theory, which we'd end with a discussion with the fellows here, Ludwig, Theo and Elias. Most welcome. Even got an English pronunciation on your name, Elias. I don't know what you prefer. I will talk today about chaos theory. It's a sort of a smooth way in understanding quantum mechanics. It's not too harsh. Once you struggle upon meeting chaos theory, it will be much more difficult. And one of the things, the factors that are very hard to understand in chaos theory is that there are no distances. Usually we perceive, I'm sorry about the pen, it can't be visible. Even worse. Usually we perceive distances like this, something that we're taught from the beginning. In between these two poles there is a meter or 10 meters or a light year. These things we take for granted, and it's actually part of our paradigm, the idea of distances as something eternal, absolute, and being out there, no matter if there is a person with a measuring device like this. Something that does not hold true. There is no distance in physics at all. The modern physics doesn't acknowledge any distance. So what we have instead is something called ratio. And ratio is deeply connected to something called fractality, or the absolute pillar of understanding when it comes to case theory is fractals. Fractal theory is an invention or an exploration by Mandelbrot, the famous mathematician. And Mandelbrot came to the conclusion that space in itself, which is the absolute foundation of distance and room and everything, is not what we think. The normal way of perceiving dimensions or the room is the Cartesian coordinate system, where you have length, width, and depth. These things actually do not exist. It's a sort of model that is perceived to be just an acronym or a generalization of something much more complex. So a more accurate way of thinking about space is the Norwegian coastline. I think maybe I mentioned that one before. Have you heard it? The Norwegian coastline, I'll take it for Ludwig then. Let's see if I can find some space. I think Ludwig was supposed to go to Norway, or was it northern Sweden, to climb a mountain. Fractality actually goes for mountains as well, but I will take the coastline. The Norwegian coastline is world famous for being very edgy. Looking a bit like this. Sorry about my bad writing skills, or drawing skills. So this is a map of Norway. And what happens in this edginess, if you sort of zoom in, you get this edginess, and then you discover more edginess inside of the edginess. And if you measure using a measuring tool, you will discover all of a sudden it's longer. And the more you zoom in, the lesser you make the distances, the more edginess you find and the more distance you find. And here comes the fun part. Even if you measure it in the normal standard way, which you used to do as a cartographer or such thing, the Norwegian coast is longer than the coast of Africa. That's sort of weird, isn't it? This small country has a coast that is longer, even in the standard measurement. Can you imagine if you go deeper and deeper down, it will be infinite. And that goes in the way of the three-dimensional idea of the Cartesian coordinate. This is so worthless, this pen. I don't know why they give this away. Come again?
The red one.
The red one? Nobody likes the red one. Oh yeah, it's better. Thanks. Almost better. So instead you have this edginess, and that means that dimensions are not 1, 2, 3. Instead there are decimals, so you have a dimension 1.1, 1.4, depending how complex this is and how much you zoom in. So the zooming in process is done by someone. So there is always someone, and who is that? That is the observer. For instance, Elias here. What he observes is in itself a measuring device. His two eyes, one eye is checking out the clarity, the focus, and the other eye is checking the angle. So his two eyes are together creating an illusion or an idea of length. But it's depending how he does it. The same thing comes to scientists, physicists. Depending which measuring tool they're using, they come to different conclusions. And they are always different. And this is why this is a segue. Segue means a sort of path going from something that is not so difficult to something that is almost impossible to understand, which is quantum mechanics. So we use this. So what do we have instead in quantum mechanics? We have the role of the observer. Depending whether you choose to measure the world as a wave or a particle, you will actually have a world which is solely made by waves or particles. You might think the difference is not that great. It is actually. It's the biggest contradiction that there ever could exist. That's the contradiction between wave and particle. They do not commute together. They do not calculate together. You get two completely different realities. Actually, when we speak about universe, we speak about particle universe. The wave universe is unknown to us. And here's one of the points of quantum mechanics. There is no distance in this reality. Everything is completely connected. All parts of the universe, no matter if they are at the longest distance there could ever be in the cosmos, I don't know how much that is, but you're speaking millions of light years, it will immediately hook up to something in this room or somewhere in Norway, or Kebnekaise for that thing, whatever. So everything is connected. That means that distance as we perceive it, that the effect diminishes. For instance, the tone of my voice is bound to diminish on the other side of this huge house. No effects in quantum mechanics diminishes. It's an illusion. It feels that way, but it's not actually true. Instead, we have something called quantum entanglement.
Do you think, does it feel that way because of Newton, or does it feel that way because of our structure of brain or consciousness?
Yes, I would say the latter. It's the perception. Our perception is built that way, as to diminish.
Before Newton?
Before Newton, even before Newton. I would say that's built into our system. Of course, this is something that is multiplied by Newton, because Newton is really insisting something is localized. Something is here, not there, which is proven to be wrong. But yeah, it's part of our perception. It wouldn't suit our survival. We're speaking about Darwin earlier. I don't know who mentioned Darwin.
Yes.
Yes. Darwin might have said it wouldn't help the evolution if some sort of animal could sense what happened in another galaxy or something like that. I don't know.
Well, in another bush, maybe.
Yeah, possibly. Yeah. But there are animals who could sense things much wider and for no apparent reason. I think dogs, they can hear so far, it doesn't even make sense for their survival. So there are exceptions, of course. I think whales, I won't slide to. I think whales have this sense of hearing things way too much longer than they have any use for. I think it's
How do we know that?
They checked it somehow, and I think it's like 1,000 miles. I'm not sure. I can't vouch for it, but it's crazy.
We can't say it has no use for them.
Well, yeah, of course, it's an open question, but as far as we know, it doesn't seem to have any obvious use. But the same goes with my thinking capacity. It's way beyond what I could use for my survival. Oh, if I have a thinking capacity, that's another question, of course. Let's see here. This is called quantum entanglement. Oh, God, these pens. It was the red one who worked, yeah. Yeah, let's see here. The red one. Quantum. And I'm going to take that versus the anti-thing to that is things are local and particular. Local. I will explain this. It doesn't make any sense in the beginning, so I'll try to explain it. Local is the idea that I'm here. As further as the sound goes, it disappears. So everything is situated here. This is where we are. And the reality which is here can be understood, yeah. Yes. And it could be used locally, and it could be used to understand other things. For instance, in a laboratory, you can look at the smallest particle, like the atoms or the molecules, or the cells, if you speak biology. And you can use that information, for instance, to take out a medicine that will help my blood pressure or... Yeah, exactly. Yeah, exactly. And this is how people used to look at nature. They looked at one species and they looked at maybe one example of that species, and I said then they can sort of use those properties to understand the whole species or whole nature. Quantum entanglement is global.
Yeah, so there is an assumption that one specimen is alike to
yeah, exactly. They are identical.
Conclusions of things that is outside the local reality you are studying.
You can extract it and use that as a generalized information of some sort. This is what people do in many subjects today. And it's based...
That's the Holy Grail.
That's the Holy Grail. That's the foundation for everything. Very good. It's the Holy Grail. You should see that Monty Python Holy Grail as well. Have you seen it? It's very good. You've seen it. Could be recommended. You've seen it as well. I can see that on your smile. It's a good one for a rainy day. Quantum entanglement says that everything is connected. So it's not particular. So we do not understand something by isolating it. So if we say this is an atom, we usually, or at least in classical thought, wanted to isolate it, take away all extras, all connections to the outside world, in order to better understand it. Isolate, essentialize, and I think here at the university, we're at something called the Liberal Arts University, would be in English maybe, the Humanisten. Here, it's very important when you write something, find out the proper meaning of the words. Write clear. I think you heard that from the teachers. What do you really mean by this? I think maybe Agneta would ask or something like that. What do you mean? What is the sense of it? So they want you to write clear. It should be down to the facts. This perception of the world is the Holy Grail. It's based in this idea that reality is local. And now we're going into the interesting stuff, the quantum entanglement. It says that the world is global. And that means that all properties coming from a singular thing, like an atom or something, is actually coming from the rest of the universe. It's not, so to speak, inside the atom. So if we isolate the atom, we will not understand more of the universe. We'll actually understand less. And that is...
so if you study a local environment, the take is that you have to, in the local environment, what makes it so as you observe it, are conditions that are outside the boundary of your local.
Yes, yes. So yeah, exactly. If I got your question right, it's like when you isolate, you take away the properties of a certain thing.
Because they are dependent on things outside.
Yeah, exactly.
All right.
Yeah. And shockingly enough, this is the big shock. It's the whole universe. And I think I mentioned this, how weird this quantum entanglement is. And I will mention here, this was some of the papers on mentioned Carlo Rovelli, the Italian physicist. And he came up with an idea of something called relational quantum mechanics. And it's an idea that when we look at a property, we stop looking at an individualized particular property. We look at the whole universe. All the relations in the whole of the universe, which is of course crazy. The universe is immense. Sometimes I heard in one lecture I had said, my God, that's huge. And somebody else said, that's bigger than God. And I say, it's much bigger than God. So all what we mean by properties goes out of the window. So all our intuitions that we use in daily life, when we go to our work, or when we commute, when we try to make a cookie or whatever, those things do not exist in reality. We just use them, and they are not true to the foundations of reality, which is this weird map of Norway. So if you zoom in, you actually get more length. Nobody would say, if I zoom in on your drinking bottle here, it would become longer. You would say it has always the same size. No, it's dependent on the measuring tool that you are using, or I am using, or we are communally using. So it's the introduction also of something called the observer. Observer-dependent reality. Observer-dependent. I think the tiredness of Theo is stretching to me now. Dependent. It's enough syllables. Observer-dependent. No, it's one too many. Dependent. No, it's... Oh. I write like this. The observer, us, are actually coming into the picture all of a sudden. So the observer's been gone almost... Somebody said in a lecture that Carlo Rovelli had, that the observer's been gone for 2,500 years. We try to get rid of him, or her, or hen, or whatever you say these days. But she came back with a vengeance. And no physics can be made or understood without bringing in you, the observer, into the picture. Isn't that strange? So we try to get rid of the observer. We've been thinking it becomes more objective. The measuring tool, our meter, whatever that is, which machine we use to detect a particle or a wave, that doesn't matter. Reality is simply out there. This is proven to be wrong. So instead we have this wholeness. All is one. So no wonder people from religious groups are attracted to quantum mechanics, because they say something similar. So many people sort of strive to understand quantum mechanics for that reason, or are attracted to it. But it is, it is actually much weirder, way much weirder. Everything is one unity, and you are the one who's creating reality. Heisenberg used to say, you create your own reality. If somebody says that in Sweden, they're bound to be locked up somewhere. This is actually physics. Isn't that interesting? Lorentz, I put down here also because he was co-founder, you could say. He was actually before Mandelbrot, but he was the one who found out that interaction, so causality, because that also is affected, because in particular local reality, causality is something simple. You have one thing that hits another, and that thing goes away in that direction. This is how I learned as an engineer when I studied mechanics and physics. That is not true either. The thing is, a very, very small, Lorentz called this, or that was later called the butterfly effect. A very, very slight influence. It could be as little as a butterfly flapping its wings can create a tropical storm 100 miles away. And that also flies into the eyes of this idea, particular and local. Particular and local builds a whole world of ideas of the more things you have, the more effect you will get. For instance, in the climate discussion now, the more carbon dioxide our factories will emit into the environment, the more negative effects we will have when it comes to warming. It is actually not completely true when it comes to quantum mechanics. A very small inducement of quantum or of carbon dioxide can have a huge effect, whereas a massive influence of carbon dioxide.
We see people talking about tipping points.
Exactly. The tipping points is a good example. Very good. You have tipping points. We don't know actually. The physicists like Carlo Rovelli and others, we don't know actually what could happen to the environment when we change the influx of carbon dioxide. There's one example. I will not make a point of this. I'm not skilled enough for that. I don't know the procedures, but it's just one example. Everything in science, in all subjects, and how you live your own life come to have an influence here. I had a particular question somebody posed yesterday. It was a guy living somewhere in America, but not in the United States. And his father had an apartment in California, and they often went there for visits. When his mother was pregnant with him, she did not visit the apartment. Or for some reason, they were born in some other country, so they didn't get American citizenship. And he has always regretted that. He didn't know why the father didn't bring the mother into the apartment and other factors. That gets very huge consequences, and he thinks it's like hazardous things. It just happened. It's just chance. The fun thing is, chance is not what we think it is, that something just happened by itself, because it goes into both directions. I will not go into much into this. We could discuss it later. But the thing is, what something ends up being can actually cause the reason why it happened. So it goes in both directions. It's a scary thing to think about, and it sort of changes everything. There is a saying from the Jesuit, the founder of the Jesuits, Ignacio of Loyola, I think it was his name. He said, the means, what is the saying now? The means...
The means...
Justify the ends?
Yes.
The means justify the ends. This is actually true in quantum mechanics. People usually criticize this and say it's all chance, and the end cannot justify how you do it. It can actually cause what happened in the past. And this is called retrocausality with a fancy name. I won't go into that either. But see, the arrow of time doesn't make any sense anymore here. Well, it's a hefty pill. Any questions? What do you say, Elias? You're the drawing guy. Can't you draw something?
Doesn't want to ruin the picture.
Well, I'm a horrible drawer. He's excellent when he's drawing skills. That's quite a difference. Can hardly see it.
No, but this is interesting. I was just a bit dumbstruck on many parts here, but could we say that quantum entanglement and particular local, are they each other's opposites, or
In a way, yeah.
they contribute to each other.
Yeah, for the presentation, I put them in opposition, but they're not truly opposites.
No, no.
But for the presentation, to easier understand them, it's better to put it this way.
Because the more you explain here, it feels like they sort of marry each other.
Yeah. Yes, exactly. Very good.
For that, well.
So you can compare it to the Norwegian coast, a very small magnification. Imagine you want to go sailing to Norway and you want to enter one of the fjords or the bays. Won't be suited, and that's in an odd way actually close to the local reality, whereas quantum entanglement is going into different magnification. Think, what is my object here? What do I want to do? What is my purpose? And then you magnify differently, but depending on what you need in your reality.
Yes, philosophically, it would be holism and reductionism, right?
Exactly. This is holism.
Depending on what you're setting out to do.
Yeah.
If you're setting out to build a bridge, particular local reality serves you very well.
Most definitely.
I was thinking the same.
And if you want to produce, for instance, I take insulin, you need to isolate this particular chemical. So it does work. So they marry each other more.
Because I was thinking about you drinking coffee, for example, that just struck me a bit because you talked.
The same coffee that Theo accused me of having dirt inside.
That is a bit quantum fundamental. No, but I was thinking, wasn't that like a particular local thing to do, drinking coffee, and because when you drink coffee, you don't think in relational terms that this drink will help me get through the day. You don't have that things in mind. You drink because it's a habit.
Maybe you do. Maybe you think I need coffee right now because I'm too tired. Maybe you think this coffee is from Southern America, and we have a wide global trading network.
Yeah, exactly. You can put it up to the global scale if you want to. Yeah.
But do you like think about the inner mechanics of your body, what the things will do the coffee when it enters your system? That
it raises my heartbeat, for instance.
Yeah, and you want that.
Well, as well, yeah. Well, thanks for mentioning it. I almost forgot the heartbeat because it's a good example of fractality. Have you heard about the heartbeat? There's something
Not
called
in this sense, I don't think.
there's something called the sinus wave, and it looks a bit like that with troughs and heights.
It shouldn't be equal, right? I remember you
Yeah.
about sometime that when it's equal in length, it means it's something is wrong.
Yeah, isn't that interesting? If you check out the heart and the sinus wave is symmetrical, most people will say, "Oh, can you imagine you go to the doctor's office?" I wouldn't mention this too much because we discussed it earlier. But you will look at the screen and you say, "Oh, that's a really nice wave. It looks really symmetrical." But the thing is, if it is symmetrical, if it doesn't have these deviances like this going up, not so deep here, and the next going up too high, going like this, being completely irregular. This is a healthy heart. It's always irregular because everything in nature is chaos theory. If it has this...
Well, through the lens of chaos theory.
Exactly.
Yeah.
If it has this shape, it is absolutely symmetrical, which is the, what do you say, the
what would look good from a
yes.
reductionist.
For reductionism, the holy grail.
Because we people always strive for the harmonious.
What we think is harmonious, but it isn't. This is
music
clear.
Is another example. Right?
Music is another example. Very good. Yeah, exactly. Yeah, music is definitely.
You don't like listening to metrometer or what is it called?
No. If you're not completely brain dead, as a friend of mine, he listens to that. But he also only have one brain cell. No, just joke. But no, and AI made pictures, for instance, like AI-made photos, it's way too symmetrical. It doesn't work. In reality, everything is asymmetrical, and the want of having it symmetrical is actually a striving from reality. Is this tendency, maybe we find this in these corridors, they want to make meaning exact. This is away from reality. Reality is irregular, edgy, and a complete surprise. So it doesn't have this a clear-cut wave of one part of history follows that, or causality, like Hume would put it. Yes, it's a wondrous world, and as Feyerabend wrote in his book, The Conquest of Abundance, it's fun to be alive. If it's not fun, it's not worth it. And the fun lies in it's completely, you can't predict it. It's not Newtonian prediction, it's not the Cartesian, completely boring world. It's a fun and marvelous world. And even in such a boring thing as a heart wave, interesting things lies. Unexpected things that cannot be predicted. And in the unpredictedness lies the stability. Isn't that marvelous? I am there. Thank you very much. You can turn it off. Cheers.